Alright guys, this is a video with another teardown of a piece of audio equipment. This time it is the Ampeg B2-RE bass guitar amplifier head. I've been using this thing for many years and I think it's a really great unit for the price. I've always been curious about the internal construction, so let's take it apart and see what's really going on in there. Let's see what's inside this baby. Interesting. Let's take a closer look. First thing you probably notice is this big ass toroidal transformer. Very nice. Wow. So we don't see any parts on this board right here. This is probably the main power amplifier board. You see the heat sinks. Those are obviously for the power amplifiers. It says SLM Electronics version 3. So looks like they may have outsourced this model, probably because it doesn't have the incredible profit margins like the other ones do. It's under $1,000. Actually, it's around $500. So that's pretty cheap for them. A lot of their bass heads go for a few $1,000s. All right. So the first thing I notice, the power cable attaches here. It has a fuse. It is interesting. So they have some suppression caps. That's good to see. Oh, very cool. An inrush current limiter. And this IEC plug is actually very nice quality. They've mounted the connector to the PCB here. And they also have a nice, integrated, what's it called? A ground block, a screw terminal. They have an integrated screw terminal right here that screws to the chassis. And on the silk screen for the actual chassis, they show that as a grounding point. So very nice. And they have a sticker in there that shows it as a ground as well. It's a reasonably sized fan. It's a Sunson 48 volt. Wow. There's some jumpers on the boards. They seem like this board in the front, most likely the preamplifier and the tone circuits, the inputs, and the display, and the graphic equalizer here. They're using a one-layer PCB. They didn't really have to do that, but I guess they're going for real cheap. I guess I'm not too surprised. They want to get their profit margin as high as possible. It's all business, baby. They have some holes in the PCB here to vent some of the heat. That's a nice design touch. All right, before we take this apart further, I don't think there's really any need to take this board out. This is the input jack. Very nice touch. They have a little, well, maybe it's not a touch, maybe it's an afterthought. They have this little insulating washer. It's more like a little standoff. It's reasonably thick, maybe a quarter of an inch maybe. That's probably just so that when you plug your cable in, there is no dead space between the front panel and this jack. So that's a nice touch. I don't know if they thought about it after. Maybe the connector was too far away from the panel. They couldn't mount it closer. So either way, they did the right thing. We have some capacitors. Oh, that's not a good thing. There are Chong capacitors, the cheapest ones they could possibly get. Come on, that's bullshit. These things are a piece of shit. Those will fail eventually. So they're attempting to stick them down to the board. I mean, that's a good thought. The board's anchored to the chassis through 4 screws. Seems reasonable. The potentiometers are nicely mounted to the front. Japan Radio Corp. I can guarantee these are quad op amps, all 4 of them. And yeah, I can guarantee these are quad op amps, and all of the different tone controls are controlling some active equalization. Standard stuff. Nothing too special there. The layout looks okay. Reasonably well done. Again, audio equipment, no service mount parts. I guess it's cheaper to have people assemble these parts in China without having any setup costs involved. Maybe. Okay. There's nothing really special here. Lots of little ceramic capacitors. There's some MOSFETs. There's 1, 2, 3, 4 MOSFETs. It seems like this MOSFET might be driving this LED. Maybe it's a clipping circuit. There's another MOSFET over here driving this LED. Okay. And there's some push button switches. One to activate the graphic equalizer. One to, forgot what that is. I think it's pre and post. Oh no, that's a limit. So you can limit the input so it doesn't overdrive the amplifier. And then this one right here, that's peak. That shows clipping. So typically you want to turn up the gain until the hardest note you pluck or pick turns this clipping LED on just for a moment. Then you have the most dynamic range of the amplifier. We have a soldered ribbon to this graphic equalizer. It just has a bunch of slider potentiometers. And then you can see the other side of the board, the traces come back. And yeah, they're doing all their tone adjustments. Okay. Well, Looks like they have an RC filter with different value capacitors for each of the bands. I guess that's how it works. Again, we have some integrated screw terminals. Very nice touch. Seems pretty sturdy. And I would have liked to see a screw maybe on here, the upper left and right corner, going to the front panel, but I'm sure the engineers were thinking that, but they probably got a pushback from marketing saying, we don't want any more screws in the front. Yeah, you see there are no screws in the front panel. So their artistic choice probably ran supreme on that decision. The highest cost item of this amplifier, I can almost guarantee you, is this toroidal transformer. It's called Keen Ocean. Huh. Has a thermal protection on it. Okay. So there's many taps. This is really nice. It's actually epoxied and wrapped in plastic. And it seems like the insulation between the windings is very nice. My guess would be this is probably half of the cost of the entire thing. I wouldn't be surprised. Really nice. Has a customer reference number, so maybe they had it custom made. Huh. So they have the option to select any input voltage. So they have the windings available for 100 volts, 110 volts, 120 volts, 200 volts, 220 volts, 240 volts. That's everything you need. It goes back to this terminal board that the mains input comes in. You see here, there are places that the quick connects aren't plugged in. So this board probably determines the configuration of the input here. Interesting. That's a smart idea, I would have to say. It's very smart. So these are all input. These are all input wires. And these 2 red and 1 green, this is the output. So again, like in a lot of audio gear, you see a bipolar supply with the center tap. We're going to take that out and we're going to take a look at that. But I'm really impressed with this transformer. No wonder it's so heavy. So here we have the main power amplifier board. I'm going to try to walk through this, see if I can identify some things, and go over the construction, what I like about it, what I don't like about it. So let's get going. First thing you're probably going to notice is the AC voltages come in at this far end. They go through this guy, which has a heat sink on it, but since this can draw quite a bit of current, this is actually a bridge rectifier. And after that, it goes into some really large electrolytic capacitors. Now these are rated at 100 volts, 3,300 microfarads each. And the brand of them is Shanghai. That's not a good sign.
some unknown brand. They're only rated to 85 degrees Celsius. Not really high quality caps. They might be, but yeah, probably not. Now, this big old heatsink was mounted, and these 8 large transistors are bent over so that the exposed metal is contacts the heatsink, and it's compression fitted. So that's a very good way of dissipating heat. Strangely enough, there's these 2 little 3-pin devices, probably transistors, and they're on their little tiny thermally conductive sponge material here, and the center pin of either one has heat shrink on it. So those are some nice attention to details. Yeah, that's a good thing to see. A lot of this stuff is definitely deliberate too, because you see the silk screen labeling. They show that that's what their intention was, so this was planned. That's definitely a good sign. So I give a thumbs up for that. These devices are, this one right here is an IRF B2-RE, International Rectifier device. And let me pull that up and see what that really is. But as I'm doing that, so it's pretty obvious. These guys are, all 4 of these are connected in parallel, and also, okay, it looks like, okay, it looks like these 4 are in parallel, but these 4 are not in parallel with those. Interesting. Okay. These resistors right here are actually what is protecting these devices from each other. And what I mean by that is, anyone who knows anything about putting FETs in parallel is they're never perfectly matched. So one will actually be stressed more than the others. And that's definitely not a thing you want. You want them to share the load. And that's exactly what these balancing resistors are doing. So that's great to see as well. And I'm assuming they got these in a batch. They probably specifically said, I want them from the same manufacturing run. Because that makes a big difference when you're paralleling devices. You want them to be as close as possible. Which is why you'll see devices that look like integrated circuits, but they're actually just sometimes matched transistors. They're on the same die, or at least in the same package. So they share their thermal experience together, if you will. This device right here says MPS A06 and then 617. That's reference designator is Q6, so it's a transistor of some sort. And this is IC1. I can almost bet you that is a temperature sensor. National Semiconductor 22AX LM35. So we're going to pull those up too. All right, so I have the data sheets pulled up for these parts, these 2 right here, and these guys right here. Now, before checking the data sheets, it's pretty obvious to know, since these guys are paralleled and these guys are paralleled, it's going to be a push-pull configuration with N-channel FETs and P-channel FETs. So, with that assumption in mind, I haven't read the data sheets, but I have them up. Okay, these four guys right here are N-channel MOSFETs. And 200 volt rating, 20 amp rating. So, okay, they're pretty powerful. Input capacitance, 1.3 nanofarads. That's pretty large. Pretty good amount of RDS on, 180 milliohms. Ooh. Yeah, no wonder that they need that big heat sink. They basically have a bunch of resistors, and you have a voltage drop across it. Well, when you have a current flowing through it, there's a voltage drop across it associated with the resistance. And that right there, that is a power dissipation right there. That's all heat. So, you don't get anything for free in this world. And this is no different here. So obviously these are going to be P-channel devices. They're P-channel 200 volt 12 amp devices. 500 milliohm RDS on. Oh my, that's insane. Wow. Yeah, that's crazy heat. Whew. And as for those other two devices, the LM35, this guy right here that I assumed was a temperature sensor, yeah, that's exactly what it is. It's a linear proportional device. So it outputs an analog voltage with a linear relationship with the temperature in degrees C. So that's a nice device. It's definitely much better than trying to use a thermistor because those are very non-linear. Cool. This guy right here, obviously it's a transistor. And so it's an NPN BJT transistor. It's rated at, okay, its HFE is 100. So that's pretty typical beta value. Power max is 625 milliwatts. So that's probably, I could probably guess that that is either amplifying the temperature sensor output. That's probably what's happening. It's either amplifying the temperature sensor output, or it's used for biasing, or it's used as a preamplifier. But I really just don't think it's used for a preamplifier. It doesn't make sense. There's a shitload of cement resistors. So it's pretty interesting. I've never seen so many cement resistors before. It's almost like they're using it as a dummy load. These are 5 watt resistors a pop, and these guys over here are 10 watt resistors. What the heck is going on? I don't know. Does anybody have any guesses? Any guesses to why they're using such ridiculously large resistors?